Okay, now we're in section 2.11 of physical chemistry. We're going to briefly talk about the molecular nature of internal energy U, also known as thermal energy. This technically has nothing to do with thermodynamics. It's actually part of statistical mechanics, which we'll be doing much later. But we're going to do it now just so you get an understanding of what's going on in our system. And of course, much later on when we get to quantum mechanics, we'll find out some much better ways to calculate this stuff. So we've been simplifying U by writing it as one quantity, but it's really the sum of a whole bunch of different types of energy. The translational energy at the molecular level, the rotational energy at the molecular level, the vibrational energy at the molecular level, the electronic energy at the molecular level, the rest mass energy of all the particles, and of course all the intermolecular forces. So the basic ones, the most important ones to us, are the translational, rotational, and vibrational. These are just functions of temperature, even at room temperature or whatever a typical system might be. Now there is also the U electronic. That's mostly constant at low to moderate temperatures, like less than 5,000 kelvins. If we were talking about really hot temperatures, then we'd have to worry about that also. Of course, the rest mass energy of all the particles, that's constant. We're not doing any nuclear chemistry here or whatever. And then, of course, intermolecular forces, this can be extremely important, but more complicated because it's a function of both temperature and pressure. Obviously, because the closer together the molecules get, the more they can attract each other. The farther apart they are, the less they attract each other. This is actually the basis for the ideal gas law, where basically in the ideal gas law, we're assuming that the molecules are so far apart because of low temperature or low pressure or high temperature that we can just ignore these intermolecular forces, so that this type of energy doesn't necessarily exist. And like I said, the calculations we're going to be doing in just a bit is going to be based on classical mechanics. Much later on in the class, then we're going to get to quantum mechanics, and we'll understand a little better how some of this stuff works. Continuing on physical chemistry, chapter 2, section 11, we're talking about the molecular energy, the molecular nature of internal energy, capital U. So remember, we have motion in all three dimensions, x, y, z here. And if you've taken enough math, you'll know that each axis represents a degree of freedom. So what we need to do is to find the internal energy molar for 1 mole of gas. I guess that's redundant. It's intensive anyway. We have 1/2 RT for each degree of freedom. So since we have motion in 3 dimensions, we have 1 degree of freedom in x, so that's 1/2 RT. 1 degree of freedom in y, that's 1/2 RT. And 1 degree of freedom in z, that's 1/2 RT. So just for the translational energy, we have 3/2 RT. And that's going to be, of course, R is your ideal gas constant, or 8.314 joules per mole Kelvin. Now, to see what that means, let's look at different species. We're going to compare one atom, such as helium, a linear molecule, such as O2, and then a non-linear molecule, like, I don't know, maybe ammonia. So each of these can have internal energy stored translationally, rotationally, or vibrationally if you're at high enough temperatures. So for any one of these, the translational energy is going to be 3/2 RT, because no matter if you're talking about an atom or a linear molecule or what, it's moving around in 3 dimensions the same, at least for a gas. Now, rotational energy, an atom doesn't have this. I'm not going to derive these quantities, just take my word for it, I guess. A linear molecule, it's got 2 halves. It's got 2 degrees of freedom, so it'll have a 2/2 RT for its internal energy, rotational. A nonlinear molecule, it'll have 3 degrees of freedom, so you'll have 3/2 RT for the rotational internal energy. Now again, vibrational energy, that is only going to be at higher temperatures, like 1500 kelvins, but I guess we can see that in this class, I don't know. So for an atom, there is no such thing as vibrational energy, so that's going to be 0. If you have a linear molecule, N, capital N, this is the number of atoms in one molecule. So 3N minus 5, that should be RT, obviously, is going to be your internal molecular energy due to vibrational energy. And then likewise, for a nonlinear molecule, it comes out to 3 times the number of atoms in the molecule minus 6 times RT for your vibrational energy. So let's look at this for a simple diatomic molecule such as nitrogen or oxygen. They're all going to be the same in this simplified model. So the internal molar energy is going to be equal to the translational energy plus the rotational energy plus the vibrational energy. They're just scalars. So you'll end up with just 3/2 RT plus RT plus RT. So the total amount of heat you could store is going to be equal to 3.5 RT. Okay, we're almost done with Chapter 2, Section 11, and Chapter 2 in general, physical chemistry. We're continuing to talk about the molecular nature of internal energy, U. Before we showed that for diatomic molecules such as nitrogen and oxygen, that the molar internal energy is equal to 3/2 RT. If you find the derivative of that with respect to temperature, well, that's the molar heat capacity constant volume. So we're going to find the derivative of 3.5 RT with respect to temperature, which just comes out to 3.5 R. Now for a carbon dioxide molecule, this is a linear molecule. Obviously it's not diatomic though, it's got 3 atoms, so N is 3. So the molar heat capacity is still 3/2 RT for the translation. It's RT for the rotation because it's a linear molecule. And then remember the formula 3n minus 5, n is 3. So we have 3 times 3 minus 5, which comes out to 4, obviously, RT. So the molar heat internal energy for carbon dioxide molecules, as a gas, remember, is 6.5 RT. And again, finding the derivative with respect to temperature gives us the heat capacity, molar, at constant volume, which would be just 6.5 R. Now, in practice, these energy levels, they're all different sizes. For example, we talked about electronic energy levels. They're only active when you're above 5,000 kelvins. That's because how much energy it can store, the change is going to be pretty high compared to the others. It's about 10 to the minus 17 joules. Now, for each one of those electronic energy levels, you've got vibrational energy levels, and that's going to be only about 10 to the 20th, 10 to the minus 20th joules. So that's why these are active at lower temperatures, like maybe 1500 kelvin. And then rotational energy, for each vibrational energy level, there's all these different rotational energy levels, and that's about 10 to the minus 23 joules. And then for each one of those, there's almost a continuum of translational energy levels, about 10 to the minus 37 joules. So really at any temperature, all your energy is going to start by going to translational energy. Okay, finishing up Chapter 2 of physical chemistry, we're talking about the molecular nature of internal energy U. I showed you last time the diagram about how within electronic levels there are vibrational levels, and within vibrational levels there are rotational levels. Just an aside, rotational, that's active in the microwave region, so it's good to know if you're going to do spectral analysis. Anyway, within the rotational levels there are translational energy levels, and those are so tiny that it's effectively a continuum. And remember, energy is equal to h Planck's constant times c, the speed of light, divided by lambda, the wavelength of the light. So, and then rotational is active even at room temperature. Finishing up Chapter 2 of physical chemistry, we're talking about the molecular nature of U, internal energy of a gas. Within electronic levels, these are the biggest. So within electronic levels, they're the rotational levels. Then within rotational levels, there are translational levels. And then within rotational levels, there are translational levels. And translational levels are so close together that it's effectively a continuum.